In today's video, we are going to be looking at our statistics unit. And with statistics, we're comparing two different variables and seeing if we can predict anything or come up with some sort of data points from our information that we are given. So we're going to be looking at scatter plots. And what a scatter plot is a graph with a bunch of dots on it. All right. They're not going to really form a straight line, but they're going to be scattered around. And we're going to try and predict using a line of best fit what kind of data points we can come up with, or try to also interpret the line of best fit in these scenarios. All right, so the line of best fit, again, a line, y equals mx plus b. It's important we know what each letter means. So the m means the rise over run, the slope. The b is the y-intercept, where it hits the y-axis. We have to be able to interpret that information from a graph. Okay, so we have Nakisha's math teacher plots students' grades on their weekly quizzes against the number of hours they say they study on a pair of coordinate axis and draws a line of best fit. So boom, there's their line of best fit. Doesn't mean that these are data points of each student. These are the data points of the students that are scattered around. This is going to help us predict certain things. So what does the y-intercept represent? So the y-intercept is where it hits the y-axis. We have to know that where x is 0, that is the y-intercept. So we're comparing quiz score and time spent on homework per week. So at 0 hours spent on homework, we can predict a quiz score of 67. Doesn't mean it's going to happen, but that's something, a rough estimate of what we could predict based on our data points, these yellow data points here. Okay, so at 0, it's going to be around 67, 68 of a quiz score. Okay, so it's important we understand how to interpret this. Now let's look at our answers. It's not how many hours a student spent studying all year. It's not the change in expected quiz score, right? It's not the change. That's probably with slope. It's not a prediction of a student's quiz score if they spend 1 hour, not 1 hour. 1 hour is over here, right? We want here 0. So a student's expected quiz score if they spend no time on their homework. Bam, no time on their homework. They're going to predict it to get a 67. All right. All right, let's look at interpreting so we interpret the y-intercept. Let's look at interpreting the slope. All right. Let's do a different scenario. All right, here we go. Riley has a part-time job at an ice skating rink selling hot cocoa. She decided to plot the number of hot cocos she sold relative to the temperature and draws a line of best fit. So as we can see from this data, as the temperature increases, the hot cocos go down and sold, right? Because when it's colder out, more hot cocos are going to be sold. We want to interpret the slope. Another word for slope is rate of change, right? Change. So when we see change, rate of change, okay, difference in the y's over x's. So we're looking at the rise over the run. So the change in the hot cocos over the temperature in degrees Fahrenheit. All right. So in these first two choices, right, good words right here, rate of change. We got to be careful, though, which one we pick. So it's the rate of change of the day's high temperature for every hot cocoa sold. That's not the rise over run. The rise, the change in the Y values, we're comparing cocos over temperature. So that's going to be our choice, second choice here, the rate of change and expected number of hot cocoa sold over, right, rise over run, the day's high temperature. Boom. Submit. Yes. All right. Let's look at another one. Another slope problem. All right. The scatter plot. All right. And the line of best fit show the length of 8 people's femur, long leg of the thigh, and their height. So what is the slope? So as looks like the change in the height affects the femur. So as the femur increases, the height also increases in most cases. Okay. So let's look at, so we're looking at for rate of change, some sort of word involving change. All right. So, and we're comparing the height over the length, the femur length. All right. So it's either these two, right? The change, the height for every one additional femur length. That sounds good. It's not the change in expected femur length, right? That's the x-axis, right? So it's going to be this one, the rise, the height over for every 1 additional centimeter of femur length. Bada boom, bam, awesome. All right, let's interpret the y value given the x. All right, so we have another femur problem. I don't want a femur problem. Here we go. A researcher studied the relationship between the number of times a certain species of cricket will chirp in 1 minute and the temperature outside. So her data is expressed in the scatter plot of line of best fit below. And what's the meaning of the y value when the x is 80? So in this data, we're looking at, all right, so when you hear crickets chirp, right? You don't hear many crickets chirp in the winter. So when it's cold out, you don't hear many chirps, but as the chirps are increasing, right, the temperature is also increasing, and that's another way you can kind of compare them. All right, so it's temperature over chirps per minute. All right. What is the y value when the x value is 80? So when the x value is 80, that's here, chirps. That means the temperature is around 64, 63, right there, right? All right. So let's see if we have that. It is the predicted temperature in Fahrenheit if the cricket has chirped 80 times. All right. That could be an answer, right? It's not the 62.8. Wait, it could be. Hold on. Let's see. The predicted temperature in Fahrenheit if the cricket has chirped 62.8 times. No. The temperature is the y values, not that one. The actual temperature in degrees Fahrenheit when the cricket has chirped 80 times. That's not the actual temperature. It's the predicted, right? This line is predicting. So you got to be careful, and it's not the actual temperature. So again, line of best fit is when we're predicting. All right. So the predicted temperature, if the chirp is, if the chirp has cricketed, it's the cricket has chirped 80 times. All right. Bada boom, bam. All right. Let's do the opposite. If we're given the y, let's evaluate the x. Don't want to chirper another problem. All right, let's look at a femur problem. Okay. Again, so we're looking at the same thing, femur length and height. And we want to, what is the meaning when the x value on the line, what is the meaning of the x value on the line when the y is 170? So when the y is 170, what does this x value mean? It's probably, we're predicting something here. So we're predicting the femur length is like 43 point something, right? 170, 43 point something. All right. So it's not the expected, so we can eliminate the expected, not the expected. Oh no, we can. I'm sorry, we can expect it, not expect it. We can't. It's not actual. I meant to say this is not an actual data point right here. This is not an actual data point here. It's expected. We're predicting it. So predicted, expected, kind of same terminology here. So the expected height, right? So when the y value is 170, so that's when the height is 170, the expected height of 170 meters when the femur has a length of 43.3, right? That's what kind of makes sense. 170, 43.3. It's going to be this one. It's not this one. The height is not 43.3. The height doesn't even go to 43.3. So wouldn't even be that one. So process elimination, it is this. So we got to be really careful with our terminology. All right. We're going to interpret one of the data points. All right. Not a femur one. Let's do. All right. Back to the math quizzes. All right. So we're trying to predict what's the point 4.75, 84.3 mean. So, right, we're comparing time spent on homework with the quiz score. So 4.75 is the hours spent on homework, right? 4.75. And the 84.3 is what this person actually got when they spent 4.75 hours on homework. This is what they got in their quiz. All right. So again, we like the words actual when we're talking about the data points. We're not expecting anything because we're not even talking about the line of best fit. We're actually, it's an actual data point. So it's a student actually spent 4.75 hours studying and got a score of 84.3. That's one zit. All right. It's not expecting, and it's not, oh man, 84.3 hours studying, got a score of 4.75. That would feel bad for that student. All right. So it's that one. And use your common sense too, like I just did. All right. Interpreting a point on the line of best fit. So now, again, we're going to be looking for predicted values or expected values, not actual values. This is not an actual data point. This is something we're trying to predict. So again, we're back to the hot cocos and the temperature. So at around 15 degrees, there's going to be around 73.8 hot cocos sold. And you can't sell 73.9 hot cocos, but we can predict somewhere around 74. Okay, so let's look at the terminology here. So when the day's high temperature is 15 degrees, that sounds good. Malik sold 73.8. Okay. That might be an actual. Let's look at the rest. When the day's temperature is 73.8, Malik sold 15 hot cocos. No, doesn't even go to 15 here. So it's not this one. When the day's high temperature is 73.8, he should expect to sell around 15. Should expect, that is on the line of best fit. So we're looking for expect or predicted. So, okay. So that's good. But again, wrong numbers, right? We want when the day's temperature is 15 degrees, they should expect to sell around 73.8 hot cocoa. So at 15 degrees, they should expect that. So again, be careful with the terminology, right? Expecting versus actual. All right. So we're going to submit that and boom. So again, I just want to reiterate the importance of making sure you know the terminology. When it's on the line of best fit, it's either predicted or expected. These points here are actual points. All right. And the slope, you're looking for words like change, rise over run, like change in the Y over the change in the X. All right, so that's it for today's video. If you have questions, let me know, and good luck with these problems. And always remember, whether you're solving for X or Y, always give math a try.